Good day and welcome to the Intelligent Vehicles demo of the Cognitive Robotics Department at TU Delft for the forum ISTS 2020. My name is Dariu Gavrila. I'm heading the Intelligent Vehicles group, and our overall mission is to improve safety, the efficiency and comfort of transportation by means of automated driving, and we're covering the full range of onboard technologies from vehicle perception, dynamics and control, and human factors. And we're in particular interested in tough environments such as the urban traffic scenario and in the interaction of the intelligent vehicle with pedestrians and cyclists. So today we are here on Green Village on TU Delft campus, and this is a living lab for sustainable innovation, and it has a bit of a urban-like touch over here, and we are going to show sequences of demos starting from basic functionality from path following to path following under and encountering static obstacles, and then move on to dynamic obstacles, early detection of pedestrians and cyclists, but also figuring out what these pedestrian cyclists will do to extract cues that will tell us how will allow us to predict the future traffic situation. And well, these demos will be presented by the PhD students that developed this work. And yeah, enough talking from my side. Let's get it on.
Okay, hello everyone. My name is Ronald Ensing. I'm a scientific software engineer in the Intelligent Vehicles group, and I will now drive towards our first starting position for the first demo scenario to pick up Oscar, one of our PhD students. And due to the corona policy, since we're in the car with multiple people, we will wear our mouth masks. Hey Oscar.
Hey.
So Dariu just introduced everything. So now the car is yours.
Yeah, sure. So hi everyone, my name is Oscar de Groot. I'm a PhD candidate in the field of motion planning. And so 3 of the demonstrations that we'll do today that involve actually autonomous driving. And so the first demo we're going to show is simply the car following the trajectory to show how the vehicle is behaving in normal conditions. And the problem with motion planning is that you have to take into account more than the current step, so you have to look ahead in the future. And that's what we're doing here on screen. So what we're doing is we're using a model of the system that we simulate forward, and we generate a number of vehicle positions that we end up in. And by optimizing those positions in the future over time, we actually find a motion plan of the vehicle. And so what we see on screen now is actually, we see a number of blue circles. Let me briefly indicate. Okay. So these blue circles are actually current motion plan of the system. And now the second thing that we see on screen is this green line, which is actually the road around this our test terrain. And we will show that the car will follow this line in the upcoming demo. So with that, I think we're ready to start the demo.
Alright, I enabled the autonomous mode and I'm now releasing the brakes.
So the first thing we can see is that the vehicle is accelerating, and it's also following the trajectory that we placed there. And so in the corners you will notice that the system is not driving at its maximum speed. So in general it should go up to 5 meters per second. But in the corners and before the corners you'll see that the vehicle is braking actually to slow down so that it can take the corners at a comfortable speed. Now we can highlight this in the upcoming corner. But now first the system brakes. It goes to 3.22 meters per second about, and then accelerates out. And so you find that this corner is actually quite comfortable for the system, and also for us in the car to take the corners. And so this is the last straight that we'll show here. That is the simplest demo that we'll do today. And with that, I think I'll give the word in a bit to my colleague, Thomas Hehn, who will show what happens if we add obstacles to this terrain.
Yeah.
Hello everyone, my name is Thomas A. And now that Oscar showed you how we drive this lap autonomously, we will now increase the difficulty a bit by adding static obstacles in our way, and we're going to evade them. And in order to do that, we of course need to detect those obstacles, and we will use a method which is called instant pixels to detect obstacles. So instant pixels are an image segmentation method, meaning that we have our stereo camera here in the car behind the windshield, outputting the image we can see on the lower left of the screen. And what we now do with this image is that we segment the image, meaning that for every pixel in the image we want to know what kind of class is it, what kind of semantic class. For example, do we look at the pedestrian or do we look at the car? And right now Oscar is walking in front of the car to demonstrate how this works, or what this looks like. So we see that Oscar in the image is now in the top left part of the screen is now colored in a different color. That means we have detected him as pedestrian, for example. Now these instant pixels, they also produce these vertical lines that we see in the segmentation image, because instant pixels are super pixels which always have a constant width, and this constant width is now shown in these vertical bars, and they only are adapted in the height of a pixel. What instant pixel also provide is this 3D position of an object, and we can see this here on the right side of the screen, where we have a 3D visualization of what is going on around the car. And we can, for example, see here now that Oscar is walking around in front of the car, and we have his 3D position by the disparity estimation of the stereo camera. So right now we see that we have a per frame detection of obstacles, but we now need to do the temporal integration of these obstacles in order to drive around them. And what we use here is a occupancy grid map, which we call a cost map in our case. And in this cost map we will now see in a different view that obstacles will be shown as black squares. So what we see right here are black squares where we detected obstacles, but we are actually only looking at a specific type of obstacles. In this case, classes car and truck. So we're going to filter out everything else because right now in this demo we just want to evade a car that is standing in our way. So I think we're good to drive.
Cool. So you can press on that screen. Yeah. Okay, all good. Ready?
Yes, please.
So I enabled the autonomous mode.
And now you can see that in the cost map, in our occupancy grid, we have detected a car. It was not in our way, so we can just drive past it. You can also see that at times our detection is a bit confused by for example the sunlight, and we have some more detections now here on the right of the cars. What we also see is that unfortunately the garage here looks a bit different than a normal garage. In this case we will classify it as a car. That is a misclassification, but it's alright because it is more important that we find the obstacle. And now we see our static obstacle in front of us, this car that is in our way, and we evade it properly by planning the motion around the car. And yes, so that was very successful, and thank you very much.
Thank you.
Okay, hello everyone, I'm Andras Palffy and I'm responsible for this next demonstration. So far you've seen two demonstrations where the car was driving itself. It was an autonomous driving demonstration. However, we work on many different things. For example, on assisted driving, when the human is still driving, as you see on my left, Ronald, but the computer is trying to help you, maybe call your attention on things that you haven't seen yet or not in time. For example, there is this car that you already see in this presentation, and now behind this car there is a pedestrian hidden. The pedestrian will step in front of us, in front of our vehicle, which is very dangerous because the human driver cannot see him in time to stop. So that's actually causing a lot of deaths around the world, and we came up with two solutions to help drivers in these situations. So we have two methods. One is camera only, so when it sees Jork or fellow PhD pedestrian in front of the car, it will give a warning with a sound alarm with a low tune. And we also have another method, which is camera and radar combined, and that's a more advanced method. That's our newly introduced method, which should pick up Jork a little bit sooner, because radar has a special property. Sometimes it can see underneath these cars because it bounces off the road. So the idea is that this new combined method is sometimes, not always, but often enough, is faster than simply using a camera. So in this demonstration you will hear two alarms, one with a high tune, that's the new method, that's the camera and radar, and one with a low tune, that's the old method, that's using camera only. And well, hopefully the new method will raise the alarm a little bit sooner. Let's see. Well, it's in a work in progress, but the idea is that if radar picks up Jork soon enough, then it can make this warning come a little bit earlier, and that little time can save lives. We can start slowing down sooner. I hope you heard our beep sooner, because it was quite a bit faster this time.
Welcome everyone to the next part of this demo. We are not only using this car to do research on autonomous vehicles, we're also looking at how in the near future we can use these technologies to support the driver. One thing that you can consider is, of course, to help the driver to pay attention to other road users and to notify him of any changes in behavior or any pedestrians and other road users that the driver has overlooked. So in this demo we will show one of those cases. So in the view you can see a green arrow which is starting at my head and pointing in the direction where I'm looking. And also we see a ellipse around Andras, which is currently green, and it will turn red whenever the car believes that my mental model of his behavior is out of date. So currently I've looked at him, he's stationary, so when I look away it will consider that I'm still assuming that he's still standing there, but not that he's changing his behavior. So if we were to start moving, and if Andras at some point while I'm looking away is starting to cross, then my mental model will go out of date until I start looking at him again. And if I were to look away again and he keeps on changing his behavior, then at some point the mental model will assume again that I'm no longer paying attention to him or know where he is or what he is doing. So I can repeat this. And yeah, that's basically the idea of this demo. I will now give the floor back to our next researcher.
My name is Ewoud, and my topic is that of path prediction. So we get in all these various types of information cues that you've seen so far, we get detections on pedestrians or cyclists, and we then want to process those into trying to predict what people plan to do. And right now we want to look at a specific scenario. So you don't see the scenario in front of you yet, but it's with a cyclist who is approaching an intersection, and at this intersection he might turn left, he might keep on cycling straight. And for the vehicle it's quite important to know which of these two it is, because if the cyclist actually turns left, he will intersect with our own trajectory, so we would need to brake, or in the worst case scenario even perform an evasive maneuver. And what we want to do here is we want to do these predictions not just based on the position and the previous positions of this cyclist, but we want to incorporate more information. We do this through a dynamic Bayesian network, and we include what we call context cues. So what we're reasoning here is a cyclist if he intends to turn left, then he or she will raise their arm, or is most likely to raise their arm. And once we have detected, then we know this cyclist probably intends to turn left, but not the moment they raise their arm, but only at the intersection. So this is something that we can then get from map information, where exactly the cyclist is with respect to the infrastructure, and then if the cyclist is at a position where you actually expect them to turn, then you will probably actually see them do so. So what you can see is this red box. Let me actually enlarge this for you guys. What you can see is this red box which shows the detection, and then inside we are estimating the skeletal pose of the cyclist. We do this through OpenPose, which is previous research by a different group from ours, but you can see this in the blue lines on top of the skeleton. And from this we are able to infer whether or not the arm was raised. You can also see that on the top left, whenever the cyclist raises his arm, then it becomes high. The nice thing to see here is also that these detections, they're not 100% reliable all the time. So when it's up, you sometimes see this fall down again. And this is the reason why we do this prediction by integrating all the information over time. It's not some sort of single shot type of information. We try to take everything into account, and when the cyclist has raised their arm somewhere in the past, this is also essential, then we can sort of expect the cyclist to turn at this intersection. The predictions will be shown by a green dotted line. You can already see one of these dots at the bottom of the cyclist right now, but yeah, the cyclist is standing still, so it appears to be a single point. And additionally, there's a circle which shows our confidence interval, because the entire setup of this dynamic Bayesian network is probabilistic, so also the future position that we estimate is a probabilistic one. To showcase how our system works is once the cyclist approaches the intersection and our system detects that he is going to intersect with our own trajectory, you will hear a high-pitched beep. And as a baseline, we also have a simple Kalman filter, which is a lower-pitched beep, which you should be able to hear then as well. What we'll be doing is we'll be driving forward a little bit slowly. The cyclist will overtake us on the right-hand side on his own lane, and then first we'll be showing the crossing scenario, the turning left scenario. So the cyclist will raise his arm and turn left. So the driver can give the signal now.
All right,
here we go. And so we start coming. The cyclist comes in sight on the left-hand side. His arm was raised, and there you see that first we detect the cyclist who have raised their arm. Then that they're turning, you hear this high-pitched beep that that our system is already detecting he's going to turn left, and the lower pitch comes, let's say, 200 to 300 milliseconds later, which is then the time we have gained to be able to respond to this situation quicker.
Okay.
And then as a comparison, what we also want to show is the scenario where the cyclist cycles straight, and show that in this case we do not get a false positive. So we do the same thing again, but this case the cyclist just goes straight, so we don't see a raised arm. And let's see how that goes. So the driver gives the signal, starts driving. We again get overtaken on the right-hand side by a cyclist. In this case, you can see that there's some uncertainty. Oh, there's also someone crossing the road in front of us. And then, okay, when he actually does turn to the left here, the signal still goes off. But during the intersection itself, there is no false positive from neither our version nor the Kalman filter, the baseline. But Now in this case, what we'll be showing is that the path planner is also able to avoid dynamic obstacles. So it's a similar type of scenario where again we have this dynamic Bayesian network trying to predict what's going to happen. Only in this case the scenario is a pedestrian who is coming from the left, who intends to cross, although we assume the vehicle has the right of way. So in this case we want to look at a different context cue. In this case it's about whether or not the pedestrian is aware of us approaching. So one of the context cues we're now looking at is whether or not the pedestrian has actually seen the vehicle. And if the pedestrian has seen the vehicle, we expect him to stop at the curbside. But if he has not seen the vehicle, he is most likely to cross in front of us, and we wish for the car to make an evasive maneuver. For safety reasons right now we're doing this one statically, meaning the car won't actually be driving, just to be on the safe side. And what we'll be showing here is how both this dynamic Bayesian network and path planner can still work together. So what you'll be seeing is the same type of predictions as with the previous demo, with a similar interface, but so now we have at the curbside, has seen vehicle, sees vehicle, and whether he's stopping or not. And you will again see the predictions, and you will see the planner reacting to those predictions. So yeah, we leave the car standing still and we signal for the pedestrian to cross. So soon you should be seeing him come from the side. It's trying to reason, but it sees that it hasn't seen the vehicle. And as you can see, the planned trajectory of the path planner tries to swerve first to the left to overtake him, but because we're standing still, the path planner can't actually perform this. So at some point it realizes that overtaking on the left side is no longer feasible, and it jumps to the back side to in that way still allow for him to continue on crossing without driving over him. And I think this is the final one, right?
Thanks a lot, Ewoud. Then I'll give the word to Dariu for concluding the demo of today.
That was it from our side. As you see, there is plenty of work, plenty of research left for us. I would like to thank the people involved, the PhD students that did this work, also the engineers, the software engineers, Frank, and especially Ronald, who was driving, who has coordinated this demo effort. If you would like to stay in touch with our research, please subscribe to our YouTube channel, Intelligent Vehicles at TU Delft. With that, I say goodbye, and I wish you best for the remainder of the ISTS 2020 forum. Goodbye.